Good day everyone. Today I am going to cover the different types of cycles in basic thermodynamics. Um, just as an ordinary recap of um, what you might have learned during your lectures. Um, so let's look at the most common of thermodynamic cycles you would find at the beginning of most textbooks. This would be the Carnot cycle. Uh, Basically, Carnot cycle is a combination of uh, isothermal and adiabatic processes. Uh, and so this is how a Carnot cycle looks. So this orange thing over here would be the isothermal part, and the red ones are the adiabatic or isotropic processes. Okay, so isothermal and adiabatic. Okay, and mathematically you can write adiabatic processes with PV power that is constant, and isothermal with PV equal to constant. So this is the Carnot process. And one of the most basic things you would notice with the Carnot process is that the slope of the adiabatic and isothermal curve, and you would find out that the slope of adiabatic is greater than the slope of the isothermal curve. Okay, I think it's over here. And let me go about explaining why that is so. So let's take the adiabatic equation, okay, and so how do you find the slope in a PV diagram like this? So mathematically you can write it as dou P by dou V. It's partial derivative because it's a function of two variables, and it's taking that way from. Okay, so the two variables will take the partial derivative. And so this is how you calculate it, and so you just start off by taking the derivative of each component. So first is this, differentiated with respect to change in volume to the gamma, okay, and then you have P as it is into gamma v power gamma by 1 is equal to 0, constant equal to 0. So after you go about the mathematics, you arrive at slope. Okay, so this is the slope of an adiabatic isometric. Okay, and similarly for an isothermal, you would get dou P by dou V for the isothermal is equal to minus P by V. Clearly, the gamma into pi is greater than, right? So this is the slope of the adiabatic. Okay, slope of the iso. So that is why you have the adiabatic. Oh, okay. I drew it all wrong. Sorry. So these are the adiabatic. Okay, and these are the isothermal. Okay, so the adiabatics are steeper than the isothermal curve, and I'll show you the proof. Okay, so this is the Carnot process, and basically you have one more similar process like the Carnot cycle, and it's called called the by the way, closed process connector would be called cycle. So there is one more called the Stirling cycle. There on the PV diagram, the Stirling cycle would look something like this. So what you would do is you would take the basic Carnot cycle, okay? And for the Stirling, you would just replace the adiabatic with a constant volume. Okay, so Stirling would look something like this. Okay, this is a Stirling cycle. Okay, so it's anti-clockwise. Got it? This is a Stirling cycle. So the thing is, this would be the heat added to a regenerator, something like a heat exchanger. Heat taken out from the regenerator. Okay, constant volume. And then you have the normal Otto cycle. Okay, so it go like the adiabatic or isentropic process, you might call it, followed up by constant volume heat addition, followed up by adiabatic expansion, followed up by constant volume heat addition. Okay, then little fast question, just a recap of what you might have learned. Okay, and then you will have something parameter called the compression ratio, right? This is V1, up to here is V2, right? Up, V1, this is V2. We have something called the compression ratio, and this is what we use to define the efficiency of the Otto cycle. Okay? Now, there is a similar kind of expression for, we have a similar expression for the breakdown cycle. I will just come to it. What the breakdown cycle is basically what you will have in a jet engine, right? It's a gas turbine process. So you have a compressor followed up by a combustion chamber, followed up by expansion nozzle, and then you would have heat rejection, goes back once again. Okay, so this case normally it's open, you show you an open thing. So this is the regenerator, right? The combustion, the fuel is added in. So this is the breakdown cycle, right? You probably know about it. How the breakdown cycle looks on a PV diagram. I'll tell you why I'm talking about the breakdown cycle right after auto cycle. So how the breakdown cycle looks on a PV diagram is pretty interesting. So you have an isentropic normal in the auto cycle. You have an isentropic followed up by a constant pressure. Okay, followed up by an isentropic, followed up by constant pressure. Okay, breakdown cycle, right? Q1 a constant, Q2 it's a constant pressure. Okay, the funny thing is the breakdown cycle has the same expression for efficiency as the auto cycle, right? Same expression, but you wouldn't use the compression ratio because the pressure is what determines the steady flow process in the breakup cycle. So you would have a term called the pressure ratio, which is the highest pressure divided by the lowest pressure, right? Starting pressure P2. So the breakup cycle will normally be expressed in terms of the pressure ratio, and it would be something like I don't remember how it goes, but it would be something like 1 RP power gamma minus 1 into something like that. Just check it out. But you don't use the compression ratio expression for the breakup cycle efficiency. So that's important. And then you have the diesel cycle. And the diesel cycle is basically called the constant pressure cycle. So you have an adiabatic followed up by constant pressure addition followed up by an adiabatic followed up by constant volume. Okay. And one more variation of this would be the dual combustion, right? So pop, 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 right? Basically a combination of the auto and the DC. They have, I covered up most of the common cycle you will look at in the thermodynamics textbook. That's it.